So my name is Bogusław Cyganek, and I came from Poland, from High University of Science and Technology. And I will be talking about fourth language, which probably you never heard of. It's quite old one, and because I'm programming for 30 years, so I came across this language when I was a young student of electronics. And now I'm preparing classes for C++, for modern C++. I recall that there is such a thing, and I started creating a program for C++ classes, and this fourth project came to my mind, and I continued, and I came with such a small footprint system, just recalling this old language to life again. So this is a twofold reason for doing this. First is to show students some modern operations in the compiler, a relatively small project like Fort, but also we can use this Fort in embedded systems. So we can recall this language again. So here's the agenda. I have some one presentation in the middle of what is Fort? So Fort was, we lost a picture of Charles Chuck, who created, Charles Moore, who created Fort in the 70s. So it had to be simple language at that time, but it has many interesting properties which can be used even today, in my opinion. The most important is it joins interpreter and compiler, so it opens some possibilities for small footprint interactive sensors, for example. And the main building block when programming Fort are words. So you can create words. There are some pre-created words, and you can combine the words. This is different, for example, a system which is compiled in from C language, and if you change something, you need to recompile. Now you can have some interaction. Yes, so this is what I said. And what is interesting, we have some variables, operators, all are defined as words. And the second notion of Fort and distinguishing from other languages is stack operations. So we have this reverse Polish notation, so we don't use parentheses, and everything is exchanged by the data set. Yes, the data stack and the word dictionary. So we will show these two operations now. So for example, here we have examples. For example, we can duplicate a topmost position on the stack. We can drop something from the stack. We can swap values on the data stack. We can make over. So it copies. I will give you some examples in a moment. We can rotate three values on the stack. And we can do whatever operations we define, certainly arithmetic, logical, but we can call some functions, and it's open something. So, for example, we have 7 on stack, then we push 2 on the stack, then we duplicate 2, so we have double 2 values on the stack. We can add, so in reverse Polish notation, we put some 2 operands and operator after the operands. So we have the result, which is 4. We can swap the values. We can make over. So we copy the last one. We can rotate them, and we can perform summation. And so it will give 8, and 8 times 7 is 56. So this is the example. And we can drop the value from the set. And the second data structure, which is the heart of Fort system, is this word dictionary implemented in a map or an ordered map in C++. I foster using C++ in embedded systems for 20 years, so with good results. But now the power of processors is enough to use even the newest C++ structure STL as well. So we can use them platforms, and come to this in a moment. So here we have an example of key values, which is, for example, drop. And if we define a new word which is double drop, so we only need to combine two drops which are previously defined. So this is also building on top of the already defined words, which is nice. So you can, for example, imagine talking to your embedded system or make some improvements without recompiling the whole system. Yeah, so that's it. And we can use whatever naming we like here. So we can use even national letters or whatever we wish here, because we are implementing this. So usually when writing for programs, here is a demonstration I can show you maybe after the time, because we don't have time now for live coding, but it is like terminal. You can define the words, and to define the words, I will show you the syntax for that in a moment. But first of all, why creating forms in modern C++? So here are the answers. As I mentioned, project started as addendum to the C++ classes, and so but soon it showed that to propagate the use of program embedded systems. Still, even if we are using Python now, we can use C++ now. C. This can be used, and we showed that and also for fun. So it's most important thing to have fun in job as well. The most important components and the roles. Here is the definition of new word, fuel consumption, and the definition of new word comes in colon and semicolon phrase. And here is a comment. If you ask the word what it does, it will show you this. And here we have the operation on the stack, because it expects two values. It computes consumption of gasoline per 100 kilometers of your car. If you put the number of liters and mileage, it multiplies by 100. It makes a swap again, and it divides, and dot is to show the result on the screen. And here is the comment. So if we have a word like this, we need to develop a data structure to hold it. So the best is to show such components, and these components will be implemented in C++, are implemented in C++ with the composite design pattern. So this is the key building block of this implementation. Yeah. And we have components. I will not go into details, just to want to show you that it is built from a couple of simple components, which are classes and mixing classes. What is important here, you can just, it is quite flexible. So you can use the key form. So it will do pre-processed, pre-compiled words. But if you wish something more, to add words, you need the fault interpreter and fault compile. So these are the three components. This is the base class, the heart, which defines the data structure. If you wish to use only precompiled words, this is enough. And if you wish to be flexible and create new words with this colon, semicolon structure, you have this. Why this is important? Because on really tiny embedded systems, you can cut parts of this structure. So here are the words. So this is big hierarchy, but actually these are simple words which perform. And the most important is this composite design pattern. You see here it is derived from the base keyword, and it is derived, so it is also the word, but it also contains some words. And we can build like macro comments with this. Very useful in embedded systems, and it works well here. So, for example, if we can process any depth of nesting ifs, do, and things like this. So how we do this is just using recursion when going from one set. So, for example, if else, here is the fourth phrase, if else then. in a colon, semicolon definition. This is my work, is the name of this work. So if we find such a branch, we process it separately. So we run the compiler again on this part. And then on this part, which can happen, be another if, and so on and so on. So the compiler is quite simple based on the recursion. And new kid on the block, the coroutines came to C++, and what appeared, actually, why I published this paper, because this is nothing special, just a student project, but it shows up that we can use for as a simple operating system in a cooperative fashion. Thanks to coroutines, this is something what I'm working on now with my students. But just very only a few words about we all know functions. We enter the function, do something, and return. And okay, there are some external results. But what are the coroutines? Coroutines are such special functions you can enter, and you can return from the middle of this coroutine and return back, resume again. So this is a mechanism for asynchronic operations, for cooperative systems, things like this, because if we have a really simple operating system, there is no use of putting Linux, for example, inside with a multi-threading. We can use something like this. So yes, so here are some examples, and the return. This is ordinary routine function. And here we have this, we can suspend and we can resume coroutine. So this is only recently added feature to C++, but we can use it to build fault which uses coroutine, certainly in the system. So here is an example of new proposition of a coroutine, which voluntarily gives up the time after 155 milliseconds. So based on this, we can build a couple of coroutines which can run, and they will suspend themselves either voluntarily or after this time. So okay, let's go to implementation. So all this was done on Linux and Windows, works fine, but we also managed with my student Wojciech Gałecki, Katarzyna Ropacz, we managed to port it. They managed. I did nothing, but they found such a device with small memory, and they put this system without the coroutines yet at that time, but it worked fine. So when connecting, it can talk with you and do some things. So our request now is how much we can go low with these values and have something operating. I don't know, embedded systems fueled by solar panels, for example, with small footprint. That we know that the more software we have, the more memory we need, the more power we need to put into device. But if we have simple sensors or simple embedded systems which don't require much computational power, we can use such tools. The project is free to use from the GitHub. And conclusions, well, is just taking some old dinosaur from the past again to teach C++, actually, modern C++. But it is quite interesting. So it's the stack operation into this reverse Polish notation, the words, and the interactive mode. This is quite useful in many applications. So although outdated, it can be still considered in some projects or small embedded platforms, Internet of Things, for example. Well, just I think is interesting project, just showing modern features like coroutines, for example, C++. So this was the original idea. Yes, and we can have this cooperative multitask task. So this was for this book, like an additional project. So that's all. Thank you very much.
Thank you very much.
So I worked in a group that the next group was using Fork many years ago. I can't say how many years ago, they were using Fork, and I was always worried how can you run this in the bare metal without any operating system? Then you just run an application with Fork, you just put it on a device like
Yes,
and be happy with that.
I'm sure it is possible, but we haven't tried in our lab. So this is another project which I'm looking for someone to pursue and do. But if you look at the components, certainly you need this background, because even if you call something from C++, STL, there are libraries working for you. So the question is, for example, if we wish to use coroutines, how much the support, down-level support, C++ environment needs. So we are limited by C++ environment here. But if you implement this in assembly, well, everything is possible. So you don't need Linux or creators below this system.
Can you do just a continuation of the question?
Yeah.
Can you do some sort of scheduling? So, for example, the main reason people go with their RTOS, is to have some type of a scheduler so that they can run fast to do something and then switch to another type. Are there primitives in Fork that allow you to do a simplified version of that?
These coroutines are.
Okay.
So you can have kind of cooperative system. So the thread has to voluntarily give up, but it is built upon such a structure. It is not preemptive, but preemption costs.
Or you have to do the preemption in the coroutine as well.
To
give up.
Yes. So this is a weaker version of. Certainly, you must be sure your coroutine will give up the time or will not hang up. Yeah, that's the point. But I remember times operating systems were far from multitasking and so this is reaching for this. But if you need multitasking, certainly go for something more serious, real time.